Refractory metals. Refractory metals are a class of metals that are extraordinarily resistant to heat and wear. The expression is mostly used in the context of materials science, metallurgy, and engineering. The definition of which elements belong to this group differs. The most common definition includes 5 elements, 2 of the 5th period and 3 of the 6th period. They all share some properties, including a melting point above 2000 degrees C and high hardness at room temperature. They are chemically inert and have a relatively high density. Their high melting points make powder metallurgy the method of choice for fabricating components from these metals. Some of their applications include tools to work metals at high temperatures, wire filaments, casting molds, and chemical reaction vessels in corrosive environments. Partly due to the high melting point, refractory metals are stable against creep deformation to very high temperatures. Most definitions of the term refractory metals list the extraordinarily high melting point as a key requirement for inclusion. By one definition, a melting point above 4000 degree F is necessary to qualify. The 5 elements niobium, molybdenum, tantalum, tungsten, and rhenium are included in all definitions, while the wider definition, including all elements with a melting point above 2123 K, includes a varying number of 9 additional elements: titanium, vanadium, chromium, zirconium, hafnium, ruthenium, rhodium, osmium, and iridium. The artificial elements, being radioactive, are never considered to be part of the refractory metals, although technetium has a melting point of 2430 K or 2157 degrees Celsius, and rutherfordium is predicted to have melting point of 2400 K or 2100 degrees Celsius. The melting point of the refractory metals are the highest for all elements except carbon, osmium, and iridium. This high melting point defines most of their applications. All the metals are body-centered cubic except rhenium, which is hexagonal close-packed. Most physical properties of the elements in this group vary significantly because they are members of different groups. Creep resistance is a key property of the refractory metals. In metals, the starting of creep correlates with the melting point of the material. The creep in aluminium alloy starts at 200 degrees C, while for refractory metals temperatures above 1500 degrees C are necessary. This resistance against deformation at high temperatures makes the refractory metals suitable against strong forces at high temperature, for example in jet engines, or tools used during forging. The refractory metals show a wide variety of chemical properties because they are members of 3 distinct groups in the periodic table. They are easily oxidized, but this reaction is slowed down in the bulk metal by the formation of stable oxide layers on the surface. Especially the oxide of rhenium is more volatile than the metal, and therefore at high temperature the stabilization against the attack of oxygen is lost, because the oxide layer evaporates. They all are relatively stable against acids. Refractory metals are used in lighting, tools, lubricants, nuclear reaction control rods, as catalysts, and for their chemical or electrical properties. Because of their high melting point, refractory metal components are never fabricated by casting. The process of powder metallurgy is used. Powders of the pure metal are compacted, heated using electric current, and further fabricated by cold working with annealing steps. Refractory metals can be worked into wire, ingots, rebars, sheets, or foil. Molybdenum-based alloys are widely used, because they are cheaper than superior tungsten alloys. The most widely used alloy of molybdenum is the titanium-zirconium molybdenum alloy TZM, composed of 0.5% titanium and 0.08% of zirconium. The alloy exhibits a higher creep resistance and strength at high temperatures, making service temperatures of above 1060 degrees C possible for the material. The high resistivity of MO30W, an alloy of 70% molybdenum and 30% tungsten, against the attack of molten zinc makes it the ideal material for casting zinc. It is also used to construct valves for molten zinc. Molybdenum is used in mercury-wetted reed relays, because molybdenum does not form amalgams and is therefore resistant to corrosion by liquid mercury. Molybdenum is the most commonly used of the refractory metals. Its most important use is as a strengthening alloy of steel. Structural tubing and piping often contains molybdenum, as do many stainless steels. Its strength at high temperatures, resistance to wear and low coefficient of friction are all properties which make it invaluable as an alloying compound. Its excellent anti-friction properties lead to its incorporation in greases and oils where reliability and performance are critical. Automotive constant velocity joints use grease containing molybdenum. The compound sticks readily to metal and forms a very hard, friction-resistant coating. Most of the world's molybdenum ore can be found in China, the USA, Chile, and Canada. Tungsten was discovered in 1781 by the Swedish chemist, Carl Wilhelm Scheele. Tungsten has the highest melting point of all metals, at 3410 degrees C. Up to 22% rhenium is alloyed with tungsten to improve its high temperature strength and corrosion resistance. Thorium as an alloying compound is used when electric arcs have to be established. The ignition is easier and the arc burns more stably than without the addition of thorium. For powder metallurgy applications, binders have to be used for the sintering process. For the production of the tungsten heavy alloy, binder mixtures of nickel and iron or nickel and copper are widely used. The tungsten content of the alloy is normally above 90%. The diffusion of the binder elements into the tungsten grains is low even at the sintering temperatures, and therefore the interior of the grains is pure tungsten. Tungsten and its alloys are often used in applications where high temperatures are present but still a high strength is necessary and the high density is not troublesome. Tungsten wire filaments provide the vast majority of household incandescent lighting, but are also common in industrial lighting as electrodes in arc lamps. Lamps get more efficient in the conversion of electric energy to light with higher temperatures, and therefore a high melting point is essential for the application as filament in incandescent light. Gas tungsten arc welding equipment uses a permanent, non-melting electrode. The high melting point and the wear resistance against the electric arc makes tungsten a suitable material for the electrode. Tungsten's high density and strength is also a key property for its use in weapon projectiles, for example as an alternative to depleted uranium for tank guns. Its high melting point makes tungsten a good material for applications like rocket nozzles, for example in the UGM-27 Polaris. Some of the applications of tungsten are not related to its refractory properties but simply to its density. For example, it is used in balance weights for planes and helicopters or for heads of golf clubs. In this application, similar dense materials like the more expensive osmium can also be used. The most common use for tungsten is as the compound tungsten carbide in drill bits, machining and cutting tools. The largest reserves of tungsten are in China, with deposits in Korea, Bolivia, Australia, and other countries. It also finds itself serving as a lubricant, antioxidant, in nozzles and bushings, as a protective coating and in many other ways. Tungsten can be found in printing inks, X-ray screens, photographic chemicals, in the processing of petroleum products, and flame-proofing of textiles. Niobium is nearly always found together with tantalum, and was named after Niobe, the daughter of the mythical Greek king Tantalus for whom tantalum was named. Niobium has many uses, some of which it shares with other refractory metals. It is unique in that it can be worked through annealing to achieve a wide range of strength and elasticity, and is the least dense of the refractory metals. It can also be found in electrolytic capacitors and in the most practical superconducting alloys. Niobium can be found in aircraft gas turbines, vacuum tubes, and nuclear reactors. An alloy used for liquid rocket thruster nozzles, such as in the main engine of the Apollo lunar modules, is C103, which consists of 89% niobium, 10% hafnium, and 1% titanium. Another niobium alloy was used for the nozzle of the Apollo service module. As niobium is oxidized at temperatures above 400 degrees C, a protective coating is necessary for these applications to prevent the alloy from becoming brittle. Tantalum is one of the most corrosion-resistant substances available. Many important uses have been found for tantalum owing to this property, particularly in the medical and surgical fields, and also in harsh acidic environments. It is also used to make superior electrolytic capacitors. Tantalum films provide the second most capacitance per volume of any substance after aerogel, and allow miniaturization of electronic components and circuitry. Many cellular phones and computers contain tantalum capacitors. Rhenium is the most recently discovered refractory metal. It is found in low concentrations with many other metals, in the ores of other refractory metals, platinum or copper ores. It is useful as an alloy to other refractory metals, where it adds ductility and tensile strength. Rhenium alloys are being used in electronic components, gyroscopes, and nuclear reactors. Rhenium finds its most important use as a catalyst. It is used as a catalyst in reactions such as alkylation, delkylation, hydrogenation, and oxidation. However, its rarity makes it the most expensive of the refractory metals. Refractory metals and alloys attract the attention of investigators because of their remarkable properties and promising practical usefulness. Physical properties of refractory metals, such as molybdenum, tantalum, and tungsten, their strength, and high temperature stability make them suitable material for hot metalworking applications and for vacuum furnace technology. Many special applications exploit these properties. For example, tungsten lamp filaments operate at temperatures up to 3073 K, and molybdenum furnace windings withstand to 2273 K. However, poor low-temperature fabricability and extreme oxidability at high temperatures are shortcomings of most refractory metals. Interactions with the environment can significantly influence their high-temperature creep strength. Application of these metals requires a protective atmosphere or coating. The refractory metal alloys of molybdenum, niobium, tantalum, and tungsten have been applied to space nuclear power systems. These systems were designed to operate at temperatures from 1350 K to approximately 1900 K. An environment must not interact with the material in question. Liquid alkali metals as the heat transfer fluids are used, as well as the ultra-high vacuum. The high temperature creep strain of alloys must be limited for them to be used. The creep strain should not exceed 1–2%. An additional complication in studying creep behavior of the refractory metals is interactions with environment, which can significantly influence the creep behavior.